Since we treat the interpolated data as if there is no samples rejected so far, there will be an overlap between valOut 3, valOut 2, and valOut 1. Nonetheless, we logically join them to form a total valOut sequence, a total sequence of valid and rejected samples. So the same sample can be rejected based on several filters at the same time. And anyway, in the resulting figure, you see specifically the valOut 3 outcome. Here is the part where we plot the outcome of the third filter. Now we go to the fourth filter, which will remove the isolated sections or isolated samples. As I have told you before, there are a few settings to be indicated for this filter specifically. It is minimal separation, which is 40 milliseconds. It is in milliseconds here. And the maximum island width of 50 milliseconds. This script is mostly borrowed from the toolbox created by Mariska Kret and colleagues. We will not dig deeply into how it works. Instead, we look at the outcome, and we will see if any islands are indeed removed after this additional step of the analysis. So if valOut 4 adds something. Not much, just a few little islands here and there, but still it can be useful if the data is more noisy. And finally, the last gap padding filter. Here we indicate the minimal and the maximum size of the gap, missing data, contiguous, and how much milliseconds or data points, since our sampling rate is 100 Hertz. So how many points do we remove backward and forward? This part is somewhat modified by me. I use a simpler expression, just a for loop, which adds the indices of the removed samples each time, and then we take just unique and sorted samples to add into valOut 5 as false, as rejected. Let's see the outcome of the filter. it rejects quite a lot. Let's zoom to see few samples. Indeed, it removes the borders of the gap if the gap is large enough. This one is not removed, and unfortunately this looks like an artifact, but it is omitted by our filters. Maybe certain parameters should be more strict, but overall you will see that the data at the end will look pretty nice. After all filters gave their results, we can look at the relative contribution of each filter into total rejection scores. It will be in the command window. For the first eye, range filter is almost 5%, speed filter 2%, deviation from smooth strand 4%, very little for isolated sections, and gap padding 5%, pretty much. And the final score of rejected samples is about 16%, which is not bad. So we repeat the same for the other eye. And now we arrive to the moment where we can decide if we use the first or the second eye, both eyes, the information from the both eyes, to estimate the differences between our experimental conditions. First, we add the first and the last point so that our interpolation works well. We will need another interpolation now with all the rejected samples interpolated, and here I propose to use cubic interpolation. In our case, the difference between the number of samples rejected as in the first eye and the second eye is less than 10%. Therefore, we will use the sum of both eyes with all samples rejected by at least one eye rejected for both. So the total value is the integration of valid outcome for one and the other eye. And in the last figure, you will see the outcome. So now in blue, you can see the valid samples from one or the other eye. In black, it is the rejected data, and in green, you see the interpolated average of the two eyes. As you can see, the artifacts related to blinks, except this one, are mostly removed, which is good. Still, in case of a lot of blinks during certain part of our data, we can reject an entire epoch. And we will speak about epoching just next.